do it in this form and say what happens, or you might have to construct it from the string. You might have to work backwards even further. So what did you figure out? So what did you figure out already, Tori? What did you figure out for a denominator? What was it?
2 to the n times n factorial.
2 to the n times n factorial? And you're doing this from starting at n equals 1. Good, I like that. I like that. Okay, so then you're trying to figure out what happens when you have 1, 3, 5.
Yeah.
Yeah, it's a challenge, isn't it? Well, first of all, what do you notice about 1, 3? You have what are 1, 3, 5 right there? Hold on one sec. Okay, so 1, 3, 5. We have odds. How do we do that? Yeah. So what? Just so we have 1 corresponds to 1. We think 2 is going to correspond to 1 and 3. 3 is going to correspond to 1, 3, and 5. So Jesse, you have an idea?
Yeah. Hold on.
What do you think?
I was catching up on that. I thought it's 1 times n minus 1 factorial, because that is factorial.
True, but it skips numbers, right?
Yeah.
So like 1 times 3 times 5 isn't 5 factorial. It's kind of 5 factorial, right? But it's 5 factorial without the 4 or the 2.
Yeah.
So it kind of looks like a factorial. So one thing you might notice is it might involve something having to do with factorial. Maybe. Does anybody know another thing? When you've dealt with odd numbers before, how do you generate a list of odd numbers?
2n plus 1.
So odd, you've also done things like 2n plus 1, or 2n minus 1 also works, right? You double it, subtract 1, you always end up with an odd number, right? Okay, so it's a challenge though, because 1 corresponds to 1 number, 2 corresponds to 2 numbers, 3 corresponds to 3 numbers. So it can't just be one of these things. So it looks like it's bringing up the observation. What happens if it's something like a factorial divided by, I think I understand what you're saying. So you're saying, how about we do something like, if you had n factorial and you wanted to divide out all of the even numbers less than it, what would it be? It would be dividing out 2, 4, 6, 8, all the way up to the thing less than it, right? So how do you write 2 times 4 times 6 times 8? What do you do? Yeah.
Is it
2 to the 1 plus 2 plus
n factorial times 2?
Is it, okay, so we have this n factorial times 2. Well, that's just twice as big, right? And this isn't twice as big. What do we think it's going to be? Yeah.
2 to the
N factorial times 2 to the n?
No, just
That's even bigger, right?
2 to
This
the
number
1.
is going to be smaller. Hold on, hold on. What'd you say?
So I want to do a parenthesis, 2n parenthesis factorial.
So you want to do this, 2n.
I only want even numbers.
I know, I understand it, but 2n factorial, that's too big, right?
No, you just go with 2 to the 1.
Hold on. Ty and then Brendan.
Denominator, I want 2n plus 1 factorial. So that they
2n plus 1, that's going to be even bigger.
oh, never mind.
This right here has to be smaller than that, right? So if you're making something that's bigger, it doesn't work, right? You're all really close. What do you think, Brendan? Any ideas?
I think.
I like this. This is with an explicit answer?
Nope.
No, they're like, well, we kind of sort of did it, but we want to stop. What do you think my favorite part of that answer is?
Dot.
No.
Yeah.
Other answers are
Not
possible. That's basically a graduate student going, I'm not going to do this. So, at least once, the limit as n goes to infinity of 2 to the what power? N plus 1, x minus 1 to the n plus 1 over. And let's just flip it over here. It's going to times n over 2n times x minus 1 to the n. Is that okay if I do that? I don't really like the compound fractions. We're going to do it anyway. So what ends up canceling here? You end up canceling this, and you're just left with the 2, correct? This ends up canceling, and you just end up with. So you end up with the limit as n goes to infinity of the absolute value of 2 times n times x minus 1, all over what on the bottom? N plus 1. Now as n goes to infinity, what happens to this right here? That goes to what? 1. So this is going to go to the absolute value of 2 times x minus 1. That's going to get infinitely close to 2 times the absolute value of x minus 1. Are you okay with that? So this right here, for this to converge, we know that that has to be less than what? It has to be less than 1 for convergence. So therefore x minus 1 has to be less than what? 1/2. X minus 1 has to be less than 1/2. So what's the radius of convergence going to be?
1/2.
Radius will be 1/2. This is not asking you to test the endpoints. This is just asking what is the radius. The radius in this case is 1/2. Because for the ratio test to guarantee convergence, when you run the ratio test, what you get has to be less than what? 1. Has to be less than 1. Has to be less than 1. Are you with me so far?
Yeah.
What if I asked you for the interval of convergence on this? The interval of convergence would be centered around what value? What's the center value for the interval of convergence here? 1. And how far out does it go? It goes out 1/2 to 3/2. And what does it go back to? It goes back 1/2 to 1/2. Now here's the thing. We know this is going to be the interval of convergence, but what's the last thing we would have to test? What's the last thing we would have to test? Are they open or closed? We'd have to test. We're not going to do this now, but test the endpoints. We'll do that later. We're not doing that now. We'd have to test the endpoints to figure out what the exact interval of convergence is. Now you got to test this. What is the first thing we have to do? Yep. We have to do. Find it. Exactly. Find the AN. Did anybody find the AN? Someone who hasn't spoken yet. Anybody have the AN? James, what do you? Actually, Ray, you haven't spoken. Yeah.
2x factorial.
2x factorial.
Yeah. X to the n.
2n.
2x factorial.
You can't do 2x. The x. No, it's x just to the n power. No, try again.
I mean 2 factorial.
2.
No, wait. No.
Yeah. So can someone help him out here?
2n plus 2 to the factorial. 2n minus 2.
Okay, hold on. We need to start with something else. Tell me what your pause. You need to tell me first what your index, where you're starting. Are you starting at 0 or 1? So everybody else, when you speak, start with that. Tori, tell me.
My n is 0.
So you're starting with n equals 0.
I have 2n factorial.
2n with parentheses around it?
Yes.
Because that's different than 2 times n factorial, everybody, right? Yeah. X to the what?
X to the n.
Yeah.
Over.
Yep.
N factorial.
Yep.
Squared.
Squared. Very nice. There it is. So here's the thing. Even if you did the proper work, if this expression isn't correct, what happens?
No points.
Well, no, not necessarily. Actually, on the AP test, if you have part A, B, C, and D, and you set it up wrong in A, but you do the proper work for B, C, and D, do you know what you get?
You only got A wrong.
You only get A wrong. Absolutely. But you better do it real well with the wrong work. With the wrong numbers, essentially. How many people agree with that? We agree? Popular?
If you start as 1.
So now, yeah. So now you need to actually do this out. So what do you end up with? Limit as n goes to infinity of 2 times n plus 1 factorial x to the n plus 1 over what? N plus 1 factorial times itself. But then what do we multiply it by? Yay! N factorial squared over what?
2n.
Yeah, 2n. Are the placement of the parentheses super important on this one?
Yes.
Super
Yes.
important. So now we get to play the fun game show. Can you cancel properly in a really, really terrible environment? Because you really want, you know things are going to cancel, right? So your subconscious is saying, cancel, make things nice. But is it really easy to cancel improperly on this?
Oh yeah.
It's super easy. So let's focus on the let's just take apart the ones we can really focus on right now. How about this and this? That goes away, right?
Yes.
And that goes away. Okay, I'm cool with that. I'm cool with that. Now I'm just going to stop at this point and write it out again, okay? And what do I end up with? I have 2n plus 2 factorial times n factorial squared. So what does n factorial squared mean? N factorial times?
And then factorial times it.
I like it that. And then what do you end up with? N plus 1 factorial, n plus 1 factorial, 2n factorial.
X, yeah, with the numerator.
And x in the numerator. Thank you. Kind of important. Thank you. Ooh, we almost lost it. So this goes away, leaving you with just n plus 1. This goes away, leaving you with just n plus 1. And then the top, this right here, and I'm going to just not write it out as a separate one. This right here, that's 2n plus 2 times 2n plus 1 times 2n times 2n minus 1 times 2n minus 2, right?
It's 2 plus 1 plus
So what ends up canceling?
2 and
Everything. So this, oh, I want the blue. Okay. That's gone because it cancels with that. So now what are you left with? The limit, and again, there's absolute value, as n goes to infinity of, what's left on top? 2n plus 2, 2n plus 1 times x all over n plus 1 squared. Now, as n goes to infinity, what does this turn into?
4.
This turns into 4 times this. And what does that need to be less than? 1. So the absolute value of x less than 4th. So the radius is 1/4. So give you a function. Let's say that function is f of x. And f of x is traveling along right here. And we're going to call this point right there a comma f of a. I could draw a tangent line at that point. You should all be feeling nice and warm and comfortable, because have you spent a lot of time finding tangent lines?
Yeah.
Little bit of time, little bit of time. So let's say I found this line. What's one reason you have found that line before? Give me one reason, Brendan. What's one reason?
The instantaneous.
Instantaneous rate of change. Another reason. Anybody have another reason why you find a tangent line at a given point?
Predicted another point.
Yeah, and that's what we're going to be doing with this, essentially. You can use the tangent line to find another point. Why would you want to use the tangent line to find another point on the function instead of using the actual function? Yeah.
Because the numbers might get really nasty.
Yeah, functions can be really nasty. Generally speaking, tangent lines, are they simpler or more complicated than the function
Much
that they're
simpler.
tangent? Usually simpler, right? Usually simpler. So what you've done before, do you remember local linearization?
Yes.
Yeah. In the neighborhood, and that's actually a proper mathematical term, even though it sounds kind of imprecise, in the neighborhood of this point, the local linearization is a decent approximation of the function, right? What is that formula? You've seen this, you should have seen this many times here. F of x is approximately going to be f of a plus f prime of a, x minus a. That's just point slope form right there. All that is point slope form. Generally speaking, the farther you get from this point, what happens? Generally speaking.
The less accurate.
The less accurate it gets. Generally speaking, the further, but for this neighborhood, it's pretty good. For this neighborhood, it's pretty good. What we're doing in 10.1 is we're learning how to write functions in a different way, because the functions themselves don't allow us, or we don't have methods for doing what we want to do to certain functions. So we take them, we take a function, we have this function, we want to do something to it. We have all these tools, but for some reason, our tools don't work. So you have two options. You either need to get more tools, or you need to change what you're looking at. If you can take something and turn it into something else that your tools work on, it's a valid method of analysis. There are certain functions that are really hard to deal with when they're written certain ways. We're essentially learning how to rewrite certain functions. All we're learning how to do is rewrite certain functions. So in this neighborhood, could you rewrite this curvy polynomial as a line? Sure. In this neighborhood, it's good enough. What are we going to do? Are we going to be approximating functions with just lines? No. We're going to be approximating functions with, not lines, with what kind of functions?
Polynomials.
Polynomials. And in particular, how long are the polynomials we're going to use?
Depends on the function.
We're going to end up looking at functions that have an infinite number of terms. And it seems like, man, we're going to take something like e to the x and turn it into a polynomial that's infinitely long. Man, that can't help us. Actually, it helps us a great deal. Because it turns it from being doable, problems that are doable, to problems that aren't doable, to problems that are doable. So what is this a picture of? This is just more of what I just wrote out. You have your function right here, you have your tangent line, you have x minus a, sorry. You're going up by a certain amount right there. This is just a tangent line at a specific point. What number do we like plugging into functions? There's a number that makes, it's kind of like the easy. We love plugging 0 into things, right? Because 0 times anything is going to be
0.
Yeah, 0 is, we love that, right? So what we first get to look at is essentially tangent lines where the function crosses the y-axis. Tangent lines where the function crosses the y-axis. That's what we get to do first. And then once we look at that point, we'll look at other points. And then instead of lines, we'll start looking at a quadratic, and then a cubic, and then eventually really, really, really high order polynomials. And hopefully there's a pattern. Do you think there's a pattern? Gosh, I hope so. I hope there's a pattern, or we're in big, big trouble. What does this look at? What is this?
Point slope form.
We just saw it. It is point slope form of a tangent line of a function when it crosses the y-axis. That's what it is. This is so if you have a function f of x, what's f prime of 0? That's the slope of the tangent line when x is equal to 0. F of 0 is the y-intercept. This is mx plus b, but in a very specific place. This is mx plus b at, well, this is just mx plus b when you're at the y-axis. Nice. The problem is, what happens as you get farther away from this point? You lose accuracy usually really quickly, right? You want it so that as you get farther away, you maintain a modicum of accuracy, right? So what do you have to do? Instead of dealing with a line, what do you have to deal with? That make this problem actually a problem. It says, we require, and I'll make it red, we require that the quadratic have the same value, the same slope, and the same second derivative at x equals 0. So what we're searching for is, we're searching for a quadratic that has the same value of cosine x at 0, the same first derivative at 0, and the same second derivative at 0. Does everybody understand what I just said out loud there?
Yeah.
So a substitution problem. So what we're saying is, here's our function right here. G of x is cosine x. So help me out here. What's g prime of x going to be? Oh, come on.
Negative sine of x.
You're like, oh, I got to crack that open. Okay, what's g double prime of x going to be? Negative cosine of x. Okay. So let's go over here. What's g of 0 going to be?
G of 0, 1.
1. So what's g prime of 0 going to be?
0.
0. And what's g double prime of 0 going to be?
Negative 1.
Negative 1. I'm making a little chart here. Let's go back over to the polynomial that's gonna be our kind of estimate polynomial. It's a local quadratization. I just made that up. It's pretty cool. So we have P2 of x is equal to some constant plus C1 of x plus C2 of x. That's kind of the grown-up way of saying ax squared plus bx plus c. What's the first derivative going to be? What happens to c naught? It's a constant, so what happens to it? It's gone. C1 plus 2 times C2x squared. You with me so far? What's P double prime 2 going to be? Oh, it's not squared anymore. Thank you. I didn't know. What's the second derivative going to be?
Just
2 times 1 times C2. Are you with me so far?
Yeah.
Okay. So what's P2 of 0? When you plug in 0 into, you know what? I'm going to move that down a little bit. Well, you can just do it. What's P2 of 0 going to be? It's just C naught. Plug in 0 right here. What's the only thing that's left?
C naught.
C naught. What's P prime 2 at 0? What's that going to be?
C1.
C1. Correct. And what's P double prime 2 at 0 going to be? 2 C2. You still with me? Okay. So we have this over here. We know that this also has to be true. We know this has to be true. And what was our qualification? Remember what our qualification was? P2 of 0 had to be the same as G of 0. P prime 2 of C1 of 0 had to be equal to G prime of 0. The function had to have the same value at 0. The first derivatives had to be equal, and so did the second derivatives. Yay! So what does that mean? What does C naught equal? 1. What does C1 equal? And what does 2C2 equal? Negative 1. Exactly. So now, hold on. Not really. Everything's relative, right? This parabola facing down, this right here is the parabola P2 of x. And it models it pretty well. If you plug that into your calculator, it actually matches pretty well. This right here was just a lot of algebra, honestly. Just a lot of algebra. Now, could we make this even more accurate by doing it to the third derivative? Yeah, you do third derivative. You could do fourth. You could do fifth. And it becomes more and more accurate. Because the higher the degree of the polynomial, what can you turn? You have more terms, right? You can have many more terms. How many terms could you have? As many as you want. So theoretically, can you keep on going? Yeah, you absolutely can. We just did this. We had f of 0, we had f prime of 0 times x, and we had the second derivative. Oh, it was over 2, right? Remember, it was 1 over 2. And actually, just to give you a hint, and it wasn't actually 2. Well, it is. It was 2 times 1. Did you see me writing that in? Does anybody want to guess what the next term is going to be if you kept this going? f3, 0 over 3 times 2 times 1, x to the cube. So instead of 3 times 2 times 1, what can you write? Yeah, exactly. Exactly. So what you can watch out, you can do this out if you really wanted to. I'll tell you right now. Could we do the same thing for this one right here? Yes, absolutely. Is it just a lot more algebra? Yes. What do you end up finding out? You end up finding that C3 is equal to what? The third derivative evaluated at 0 over what? 3 factorial times x to the third. So you can keep on doing the algebra if you want to. And then what's the real kicker here? You end up with this. Here it is. Oh, there's no x on the c term, sorry. The c gets multiplied by that. You end up with this right here. Cn is f. Does that mean to the n power? No. If you have it in parentheses, what does it mean? The derivative, the nth derivative. The nth derivative. I can guarantee 2 or 3 of you on one of these tests is going to swear something instead of taking a second derivative. You're going to be very angry at me, and you're like, I can't find inflection points. You're a horrible person, and then it was a derivative, and then you'll feel bad about that. Let's just avoid that, okay? Over n factorial 0. So what does this mean? It means we can now state this right here. Taylor polynomial of degree n approximating f of x for x near 0. This is a really, really good approximation for the function f of x when you're around 0. You can go as far as you want. The farther you go, the accuracy improves. The farther you go, the accuracy improves. But the key thing is, what is this around? This function can travel anywhere, right? This is only the approximation around what value? 0. So there's one more thing that we need to further generalize. We first did a line, then we did a quadratic, then we did a cubic, and now we're going to the nth power, right? But we're still stuck around 0. Theoretically, would we like to be able to estimate other places? Yes. Yeah, we would. Yeah, we would. So before we do that, let's just check in here. Can someone read off to me the first few terms? So what's it going to be, everybody? Hold on. Who's going to? What is it?
0
plus.
0 plus 1 over 2x.
1 over 2x. Yep.
Minus 1 over 3 factorial times x to the third.
1 over 3 factorial times x to the third. 1 over 3 factorial times x to the third. Let's just do 1 over 2 factorial. Yep. Plus what?
1 over 5 factorial x to the 5.
X to the 5. Yep.
Minus 1 over 7 factorial to the x to the 7.
Yeah, and there's some terms missing there because they're zeros, right? Yeah. But this right here, you would answer the question, absolutely, and you could delete that. That's fine, right there. So what a common question is on the AP test, it'll ask you, what are the first 4 non-zero terms? These would be the first 4 non-zero terms of the Taylor polynomial of sine of x around what?
0.
Around 0.
It's around pi over 3.
No. Hold on. That's not what it's asking you, James. It's saying compare the value of the Taylor polynomial with the true value. You're then using this to approximate. It's not saying around pi over 3. It's not saying around it. It's saying use this to estimate. Estimate. So this right here is an estimation of sine of x around 0. You could then use it to try to estimate the value of pi over 3 without using the sine function. That's what it's asking you to do. Before I say anything else, listen, look, first of all, the function we're dealing with is what? F of x is sine of x. Okay, let's just do it at what's f prime? Cosine x. F double prime. Negative sine x. F triple prime. Negative cosine x. Gotta write that out properly. Negative cosine x. F4, what's that? Sine x, and are we back to the beginning? So what you literally have to do first, write them out. It's super helpful. You get cosine x. What's the most common thing people get wrong when they're writing these out?
Positive and
The
negative.
positive and negatives, they make some small mistake. And what's the last one going to be here? Negative cosine x, right? But then what do you have to do at each of these? So what's f of 0? 0. Then you have to do f prime of 0. What's that? 1. What's f double, what's that of 0? Sorry. 0. Then what's the next one going to be? Negative 1. And then f4. And then it keeps going, right? But you have to write all of these out. 0. So we plug that in. F prime of 0 is 1. 1x. Yep. Plus f double prime of 0 is 0 over 2 factorial times x squared. Plus, and we can do the next one now, the f triple prime of 0 over 3 factorial times x cubed. What's f triple prime of 0? Negative 1 over 3 factorial. Right, exactly. So you can just fill this in. So are there a few things missing here? Well, this right here should actually just be what? Just be x. You'll notice it's really common when we're doing these Taylor polynomials with really core functions. Is sine x considered a core function? Yes. We have x. So what's really out front of there? 1 over 1 factorial, right? So 1 over 1 factorial x minus 1 over 3 factorial x cubed plus 1 over 5 factorial x to the fifth plus 1 over 7 factorial x to the seventh. What do you think the next one's going to be?
Plus 1 over 9 factorial.
X to the 9. Exactly. Yes, James.
Henry.
Henry. 你的名字不是 Henry.
Sorry.
Exactly. Literally start that. And don't be lazy about it because if you do, things go bad. So what's f prime of x going to be? X to the negative 1. What's f double prime going to be? Negative x to the negative 2. And what's f3 going to be? 2x to the negative 3, right? And what's f4 going to be? Negative 6x to the negative 4. So then f of 0, what's that? What's ln of 0?
Undefined.
Oh, wait. Hold on. We just saved ourselves because what is ln of 0?
Undefined.
It's undefined. We wouldn't be able to do this around 0, right? How can we approximate something that doesn't exist? That's not what the That's not what the question is asking. What's it asking? Near
1.
Oh, what's f of 1? What's ln of 1? 0. So what's f prime of 1? 1. What's f double prime of 1? Negative 1. What's f triple prime of 1? 2. And what's f 4 prime of 1? Negative 6. All we have to do is now plug in. That's all we're doing now. So construct the Taylor polynomial of degree 4. What's f of 1 going to be? Oh, it's 0 plus, what's f prime of a? What's f prime of a? In this case, a was 1. So it's 1 again. So it's 1. Look up here. We just figured f prime of a was 1. What do we multiply it by? X minus 1. It was just x before because it was x minus 0. Plus, what's f double prime? Minus 1. So it's going to be plus negative 1 over what? 2 factorial times x minus 1 squared. What do we have to add to this? Well, what's the next one? Oh, it's going to be negative. Is it negative 1, right? No, it's 2. Thank you. 2 over x minus 1 to the... Are we done yet? No, because what degree are we supposed to go to? And what degree are we at now? 3. What's the next one going to be? Oh, negative 6 over 4 factorial x minus 1 to the 4. There it is, right there, everybody. This right here is the Taylor polynomial of degree 4 approximating the function ln x for x near 1. Yes, James? Yeah. So you end up with 1 plus x plus 1 over 2 factorial x squared plus 1 over 3 factorial x to the third plus all the way up to 1 over what? What's the last term going to be if you want this to be of degree 10? It's going to be x to the 10 10 factorial. There it is. Hey, look! You now know the Taylor polynomial of degree 10 approximately b dx around 0.
That sounds so cool. Yeah. That's a great trick right there.
That's what you gotta do next week at a dance. You wanna like make a pass it, you're like, man, I'm gonna tell you about Taylor polynomials. Yeah.
Like, shows you.
Shows you. Okay, kids, you can pack up. Homework is listed in Schoology. Kick his butt. Oh, if you haven't done it, well, there's 4 of you that still haven't done the class survey. If you could do that, that's great. You like this stuff? Huh?
This is getting fun. Much better than finding these coordinates with diamonds.
Fun is not the word I would use. Oh, it's fun. I'm not going to use it. This is very, very low. Yeah, you know what? Oh boy.
Your name is Matt May, Matt May.
It's so English. You can't take the point. That's why it's you don't have it as a smash. That's fine. But I don't have it. It's literally it's not a 0, it's not
The issue is that factorial of 0 is 1.
Yeah, work on it. It's cool. And I was really assuming there was some cool solution to it. And the book killed me. The book killed me. Oh man.